All right, guys. So the next question we're going to solve is in our packet. It starts on number 23. It's got this picture and sort of this blacked out thing didn't come across well on the PDF. I'll read it real quick. And this is an important one because this is actually sort of similar to what we're going to do in the project when we get back from distance learning. So it says the top of a 3/16 inch acrylic testing box is covered with an unknown half-inch insulation material. It's black. The dimensions of the box are 10 inch by 10 inch on each side. The sides are wrapped in a control insulating material blue so that almost all heat loss is through the 10 inch by 10 inch unknown insulating material at the top of the box. Assume no heat is lost from the sides or the of the box. Determine the thermal conductivity for the insulating material if a 25-watt bulb is used to heat the box. You may assume that the only heat loss from the box occurs through the 10 by 10 test area. The bulb maintains the inside temperature of 10 degrees higher than the outside temperature. So this is a picture of the apparatus that they're actually talking about. This is what we're going to use when we test our insulating material when we come back to class. What we have here is we have a light bulb in here that's providing the energy source. It's providing the energy at 25 joules per second, so that's 25 watts. We're going to cover it with some insulating material that we want to test, and we're going to try to calculate, based on some measurements, what its thermal conductivity is. So, think about what's happening. It's going to be warmer in here because we're always putting some energy into the box itself. It's insulated on the sides, so we're going to assume it's going to lose just through the top. And of course, we will lose some energy through the top. So if we can maintain a difference in temperature between the outside air and the inside air, the greater the difference in temperature, the greater that thing's ability to insulate. So luckily, in terms of the equations, it's pretty simple. We're just going to use our equation for K, thermal conductivity, straight off of our equation sheet here. And it looks like this. So it's based on P, the power or the energy source, right, which is our 25-watt bulb. It's based on L, which is the thickness. Now here's the pain in this problem. P is in watts or in joules per second. That's an SI unit. So that means all of our sizes need to be from inches into SI units of meters, and I've done that for you. So a 10 by 10 inch, if we convert that into meters, is 0.065 meters squared. It would be 100 square inches. That's 0.065 meters squared. So the area goes down there. L is the thickness. They said that it's going to be half an inch of insulation. A half inch in meters is 0.0127 meters, so that's where L is. And then this insulating material has the ability to maintain a difference of 10 degrees. So 10 degrees Celsius would go here. We can leave it in Celsius for this because we're talking about a difference in temperature between the inside of the box and the outside of the box. So even if we had it converted those two temperatures to Kelvin, the difference would still be 10 Kelvin. So when we put those values in, our thermal conductivity comes out to be about 0.49. Strange units, it would be watts per meter per degree Celsius, or sometimes you might see it as joule per second per meter per degree Celsius. Obviously, the higher this value is, the greater its ability to actually let energy or heat flow through it. So if we want something to be a good insulator, we want this value to be relatively low.